Hello everyone. Welcome to today's data learning seminar. So today we're very happy to have Dr. Felipe Bravo from the University of Chile. And today he will talk about tackling fairness, change, and polysemy in word embeddings. So Felipe, I will lead the audience with you.
Oh, thank you very much. Thanks, Sibo, for the introduction. Also, thanks, Cesar, for inviting me. I'm very happy to share my research with you guys there in the UK. So yes, this is a talk. So my idea is first to introduce a bit what word embeddings are. I'm not sure how familiar are you with NLP literature. So I will give a brief introduction of what word embeddings are, and then I will show you some limitations of these tools. And I will briefly discuss 3 research projects I've been involved at tackling each of these problems. And these problems are the same, are shown in the title of this talk, which are fairness, change, and polysemy. Okay. So what are word embeddings? So in NLP, in modern natural language processing, we need to find a way to map words, which are discrete objects that are the basis of language, into continuous representations that we can operate with. So what we usually do is to project words into an embedding space, which is a vector continuous dense space. And we hope that when we do that, we can convert words from isolated discrete objects into continuous vectors that can in some way, some sense, capture semantic and syntactic properties of words. And nowadays, any modern NLP system, like any translator, sentiment analysis system, question answering system, will have word embeddings in some part of the system. So they are a core component of NLP systems. So classical examples you can observe from word embeddings is that they can be trained from unlabeled corpora, from large unlabeled corpora, large collections of documents. You can automatically obtain these representations, and they can capture very interesting properties like semantic properties, like the king is to queen, like man is to woman. You can make operations with these vectors, like using Euclidean distance or cosine similarities. You can also obtain relationships like syntactic relationships, like in verb tense, like gerund form and past tense form. And you can also obtain other associations in terms of capital and countries, like Spain is to Madrid, like Italy is to Rome, and so on. So that's quite magical. So you train these vectors from unlabeled data, and you obtain these vectors, and you can play with them, and you can easily observe that they are capturing very interesting properties of language. Okay, they're based on theory. They're based on the distributional hypothesis, which is a theory of semantic language, which basically says that the meaning of words is determined by the context in which words occur. So that will imply that words occurring in similar contexts will have similar meanings. So you will expect if the word cat and dog are used in similar contexts, they should be more similar to each other than the word, I don't know, burger. Okay, that's the idea. So all methods and algorithms for training word embeddings are based on this paradigm, on this hypothesis. Okay. So the idea, so in a very, very broad way, the idea is that you have documents, like the document gave a research talk in Boston, had a science lecture in Seattle. You will expect that similar words that occur in similar contexts receive similar vectors. So here we have a 2-dimensional representation, and you will expect that Seattle and Boston are similar with each other, had and gave are similar, lecture and talk are similar, research and science are similar. And you expect you have a large corpora, these vectors end up aligning themselves to capture the representations you want. So how you build them? Usually you build them, most of them are built using neural networks, architectures, and unlabeled corpora. That's quite handy because unlabeled corpora is quite easy to obtain. You can obtain it from books, papers, Wikipedia, tweets, the web. So you don't need to annotate documents here to obtain the representations. And usually the way they are obtained is by formulating an architecture using a neural network in which there is a predictive task, usually like predicting a missing word within a context of windows. And the embeddings, these vectors will naturally arise at in some part of the parameter space. And the idea is that they arise after the training, and then you can use them for any other task. So there are many different approaches. Popular ones are skipgram negative sampling, continuous tag of words. They're both form part of this popular word2vec software package. But there are others like Glow, FastText, and there are others that are more sophisticated that are contextualized, like Bird and Elmo. But I won't talk too much about them, at least in the first part of this talk. So briefly, this is the idea of the skipgram model in a very simplified way. So the idea is that you have sentences and you iterate a window through these sentences of words. The size of the window is a parameter of the user, and you try to, given a center word, try to predict the surrounding words within a window. So for example, you have the quick brown fox, and if brown is the center word, you try to predict the word quick and fox. And this is done by projecting a one-hot representation of the word. A one-hot representation is a vector in which you have 0 entries for all values except for the word that you have you're operating at in this particular moment, and you project them using an embedding matrix. And this embedding matrix performs all the mapping between the one-hot vectors into the dense representations. The idea that these things are parameters of the model, so they're initialized randomly. But after training, after trying to make the prediction of predicting surrounding words, thanks to the distributional hypothesis, these vectors start capturing semantic and syntactic properties. Now that's the main idea. Okay, so this is in a very, 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 very condensed way what a word embedding is. But they have 3 very well-known and well-studied limitations, especially the embeddings we have seen so far, which are known as static embeddings. So the first thing is fairness. Many studies have shown that the distributional hypothesis preserves some stereotypical social biases from the corpus they were built on, and they can go against many identity groups, social identity groups like gender groups, ethnicity groups, religions, and so on. So these are very well-known and studied problem. Another is change. The way these things are trained is it's like a batch learning setting. So you train them once, and then you get the representation. And that means that they ignore words not observed during training, and they're also unable to capture semantic drifts. Words in long periods of time can change their meaning over time or acquire new meanings. Like the word apple maybe now has the meaning associated with a company that didn't have, let's say, 70 years ago. So when you want to study these representations for lexicographic studies or semantic change, the way they're framed is not very useful. And also, even in social media, you can observe some drastic changes. When some drastic event happens, you can see new expressions like hashtags, or even the meaning of one particular concept can change given some particular event. So we have fairness, we have change, and the third problem that is quite also relevant is that as many words are Polissimus. That means they can have more than one meaning. Like the word apple can mean a company or a fruit. The word bank can be the institution in which we deposit money, or can be the river bank. So that can happens a lot in language. And as you have one vector per word, you end up conflating these multiple meanings into one single vector. And this can also be a problem, and so you can observe some undesired associations, like, I don't know, the word right, the word left being close to wrong, and that's because left is close to right and wrong, and you end up getting these associations that are not very sensitive. Okay, sensitive. So with this, so now I have finished the first part of the talk, trying to introduce what word embeddings are and 3 limitations of them. Now I'll proceed to briefly discuss 3 research projects I've been involved, tackling each of these problems. So let's start with fairness. Okay. So as I said before, so word embeddings usually can exhibit undesirable associations for social identity groups. So in the same way as these nice associations are observed, you can observe not very nice associations. Some awful associations can also be observed, like that have been reported in many studies, like black is to criminal as Caucasian is to police, Man is to doctor as human is to nurse. Man is to computer programmer as human is to homemaker. So embeddings can learn these things from the data, from the corpora. And the problem of this is that when you use these embeddings trained on corpora, which contain these social biases, they can end up amplifying the biases when they're used in other downstream systems, like recruitment systems for jobs, translation, recommendation. So this is a big problem. So we observe that there have been several approaches for both measuring the fairness, the biases and fairness of word embeddings, and also to mitigate them. So what we observe is that metrics are, we try to, what I'm talking now, what we talk now is how we try to standardize existing approaches to measure these biases. Okay, so there are many metrics that have been proposed in the literature, like, for example, WEAT, which is a metric that measures the degree of association between two sets of target words and two sets of attribute words. So, for example, the paper tried to measure biases regarding ethnicity in relation to pleasant and unpleasant words, and gender relation to occupations. So, for example, if male words or female words are more associated with STEM careers or art careers, or if some ethnicities are more associated with pleasant words or unpleasant words. We have another paper called R&D, which compares embeddings related to two different social groups against a set of neutral words. So this paper evaluated gender and ethnic biases in embeddings trained over different time periods. We have another metric called RNSP that measures the KL divergence between the negative sentiment probability and of the embeddings and a uniform distribution. So here the idea is that if you have some sentiment words like positive and negative words, you can train a logistic regression to predict the sentiment of words. And then you can apply that model to some identity words like national origin identity words, American, Mexican, Canadian, and you can obtain from the logistic regression a probability score of each of these terms. And then you can normalize that to these scores to sum up one and treat it as a probability distribution. So you would expect that an unbiased model will obtain a distribution similar to a uniform distribution. So you will expect that most sentiment scores will be 0.5 for each national identity term. So the idea of this metric is to compare what you obtain from your embeddings with its uniform distribution and turn this into a metric using KL divergence. So what do we observe here? So although all these metrics have similar goals, the goal is to measure the amount of bias exhibit in each embedding model. Embedding model, what I mean with embedding model is what you obtain after training the model. So after you feed the algorithm, like negative sampling, negative sampling, into the corpus, you obtain this representation. The idea is to measure the fairness of this representation. So the metrics I described in this slide show that all these methods try to do the same thing, but they're different. They differ a lot. They differ first in the kind of inputs they receive. Some methods are pairs of words, in other methods are sets of words, sometimes there are multiple sets of words. Their outputs are also not compatible with each other. Sometimes they're real numbers, positive numbers, or they can be restricted into the 0-1 range. So what we wanted to do was to propose a framework that we call the Word Embedding Fairness Evaluation Framework to try to measure and mitigate bias in word embeddings and try to formalize the metrics into a unified framework. So our proposal was to try to standardize all these proposals into a single unified framework that could allow us to then compare things. We'll say, establish, for example, if one embedding is more biased than other according to metric A, B, C, and see if these metrics tend to agree with each other or not. So our idea was to propose a standardization framework. How we did it? We encapsulate first all the input words of these metrics into objects called queries. We call a query an object, a mathematical formal object that encapsulates the different types of inputs that an embedding fairness metric can receive. And then we try to formalize how these metrics operate and obtain a fairness score. And then we allow to rank various embeddings models by aggregating these scores. We proposed a way to make aggregation, which is based on transforming the scores into rankings by using order relationship that can allow a more clean comparison between the scores. So these are the main building blocks of what we did of WEFE. So we have these target sets that we define. A target set is a set of words with words denoting a particular social group. For example, you have the group women, and you will receive words like she, woman, girl. For the group men, you will have words like he, man, boy. So we refer to target sets as the words that describe a social group, okay, representative of what a social group is. And on the other hand, we have attribute sets that are words representing attitudes, characteristics, traits, occupational fields that can be associated with individuals from any social group. For example, you can have words like science, math, physics, chemistry, art, poetry, dance, literature, but you can have positive words here, negative words as well. So the idea is here to encapsulate all the words that in an unbiased world, you would expect them not to be more associated with one group to another. So usually when you have some prejudices against social groups, you usually put these prejudices into one of these attribute sets, and you expect them not in an unbiased representation that no single social group should be more associated with one attribute than another. But this is exactly what happens. So in a sense, all metrics try to quantify how the different target sets relate with these attribute sets. Okay. But they can do it in different ways. It's quite different what is done in WED, in which all the operation is done by computing centroids of vectors and computing differences and obtaining scores in this way. And RNSB, for example, is completely different. You have a classifier, you obtain a probability distribution, and you scale divergence to measure that. So they're very different. But we try to first, so we define a query as this object that receives a per Q, and we receive two sets, T and A, in which T is a set of target word sets and A is a set of attribute sets. So in that way, we can obtain a query, for example, that can be performed to the WED method will be this query. Receives as the target set, receives words for women, for men, and then for attributes, words for science and art. Okay. So queries are the main building blocks of using inferring metrics. And what we formalize is that each different first metric can be defined with a query template, which is defined with a pair of natural values T and A, and indicating the cardinality sets of T and A. For example, in the case of WED, in which we have two target words, two target groups, and two attribute groups, the cardinality will be 2 and 2. So that will be the query template of WED. But then R&D, for example, in which the input is two groups and one set of attributes will be 2, 1. And for example, in this RNSB, we have positive words and negative words will be the two attributes, but we can have n different target groups. So the query template here will be n, 2. Okay. So this is quite interesting. So with the idea of query template, we manage, and queries, we manage to standardize all different inputs that fairness metric could receive. And then to try to make to give some sense of how these metrics operate, we say that each metric must be equipped with an total order relation F that establishes what is to be considered as less biased. So for example, in metrics like Kn divergence, what is less biased correspond to the absolute value. But for example, in other metrics, it's not the absolute value, but it's the whole thing, it's the real value. It's the raw output. So with this order relationship, we can equip the metrics with that, so we can know how to interpret when a score is indicates more bias or less bias. Putting this all together, we can now, for example, have a bunch of queries, a bunch of metrics, and apply the same queries to different metrics for the same embedding and obtain different scores using different approaches. And as we have this ordered relationship, we can then rank the embeddings according to different criteria. And then we can aggregate these rankings and obtain aggregated scores. And in this way, we can compare different resources, these embeddings, according to different criteria like gender, ethnicity, religion, and also different metrics, and make all different approaches more comparable. So that's what we did. We carry out a case study in which we took the different embeddings that were available on the web, free resources trained on different corpora and different methods. And we performed these queries based on the obtained from the studies of these different papers, these different metrics. We try to reproduce these methods, but using our framework. And we were able now to obtain this kind of rankings. So the size of each bar here correspond to the ranking. So the wider the bar, the lower the ranking, so more bias. And we were able to observe that the metrics tend to correlate with each other quite a lot, especially for gender. They were in line with each other. And we were able now to aggregate these scores and able to produce a full ranking of resources in terms of fairness. So we could observe, for example, that ConceptNet, which is an embedding method that not only operates on corpora, but also exploits knowledge bases, was much more fair than other resources. And this was consistent across many metrics. That's the idea of WEF. And of course, the study had many more caveats, but I won't go into the details in this talk because I want to talk about different things. But we released WEF as an open source toolkit. Maybe I can show you my screen. And it's open source. It can implement many different things. It's on GitHub. I will try to show it this thing here. WEF embeddings. Let me find. So this is WEF. So it's hosted here. It can be installed easily on Python using pip install and common apps with multiple metrics and tutorials, and also with implements lots of methods to reduce the fairness. So what I talked to now was about measurement of fairness, but there are also other approaches for mitigating these models. So I invite you guys to take a look at the software, to install it. It's open source. We also always welcome people to contribute, and we also have received many contributions from users. Okay, that's it. That was the first part of the talk, talking about fairness. Now we'll talk about change and polysemy. Remember that the talk tries to show how to tackle 3 different problems of word embeddings. So what I talked so far was about fairness. Now let's go to talk about dynamicness. So as I said before, a problem of these embeddings is that they're static. So you train them once and that's what you got, but language is dynamic. New words can arise in social media. Words can change their meaning over time. So what we proposed here was try to train these embeddings in a dynamic fashion using a stream approach. So how to try to use ideas from stream machine learning, which have a stream of data. So that's quite different from the batch approach. Data is infinite. Models are always able to make predictions. You can't rely on many pre-processing operations because everything must be done on the fly. So our idea was to adapt existing static embeddings models to a streaming setting in which they are always training and being updated, and try to do that to make a sentiment lexicon. So what is a sentiment lexicon? Is when you map word embeddings or words actually into affective categories like positive, negative, anger, and fear. They are very useful, this kind of resources, to classify tweets or sentences into sentiment or affective categories. The usual way to obtain these lexicons is by training word embeddings and then using these embeddings as the feature space, and then use a seed lexicon of some words that you know their sentiment, like love, hate, as labels. You label some of your embeddings, you train a model, and then you use your model to make predictions on all the unknown words, and so you can get a full lexicon of the whole vocabulary. That's what usually people do to build these lexicons. But this approach is very static. So So in that way, sentiment lexicons are unable to capture, for example, sentiment of new hashtags that are happening. Or sometimes it's quite interesting when you have an entity word and you want to track its sentiment over time. If you do it in a static way, you can do that. So our idea was to adapt existing embedding approaches to a dynamic setting. We use the word context matrix, which is a predecessor of the more dense neural network-based approaches, but they have shown to be equivalent. So basically what you have here is you have a big matrix in which each word is a row, and you have contexts, which are usually other words in which the word occurs. And you have some scores that correspond to the associations between words and contexts, and they're usually computed using something called point-wise mutual information. So our idea was to do this fully incrementally. So we proposed an incremental variation of the point-wise mutual information, in which every time as tokens arrive, the matrix gets updated. If a new word occurs, you add a new row into this matrix, and all these associations are always being updated as new words arrive. And also the idea is to have a lexicon of some words with known sentiment, and you have also an incremental classifier, like an incremental logistic regression trained with SGD. So every time you see a word that you know the label, you also update the classifier. So you update. So that's the whole pipeline. You have a stream of text. Every time you receive a new sentence, like a tweet, you update your word vectors by traversing a window, context window through the content. You update all the matrix. Then if the word is labeled, you update your classifier. And every time you see a word that is unknown, you update your predictions. So you are constantly learning, updating your representation, and also constantly updating your model, your predictive model. That was the idea. So that's what we did. We decided this algorithm, and we proposed a way to evaluate this. So what idea was, okay, how you can control actually semantic change. It's not trivial. It's not trivial to identify words that have changed sentiment or meaning over time. Sometimes these changes take a long time to happen. So we decided, let's try to simulate this. So how we did it? We created synthetic data. Basically, we say at some moment of the stream, we will say that a drift will happen, and then we can control how abrupt how strong this change will be, the degree of this change, and that will be how many words will change its sentiment. And then after that, some words are chosen from the test set and are swapped, and their sentiment is swapped. For example, you say the word love was positive, now at this moment will be negative. And how you do that? You say now the new meaning of love will be another negative word, let's say hate. And then you pick some sentences with the word hate, and you replace the word love in it. So in this way, you're simulating a new meaning. Okay, and you will expect then, and if these embeddings are incremental, at some moment they will adapt themselves to the change, and they will start making right predictions in terms of sentiment. So this is what we did. So here's our example of our stream. This is the accuracy over time, predicting the sentiment of words. And at this moment, we induce a change, 30% of change. And we show that our approach of these incremental embeddings, even though at the moment of the change, you observe a degradation in performance, you see that after a certain amount of time, the representation can learn the new meaning, and the accuracy gets stable again. So here the blue line represents the whole stream without change, and the orange line represents when we induce this change at this moment of the stream. This is the overall accuracy, but we will also study individual changes. So this is the word death that was replaced by a positive word. So this is the whole stream without the change. You see how this SGD managed to learn the sentiment after certain observations of the word. So at this moment, it's quite clear that the word is negative. So this score is the sum. What is it? It's the difference of the positive probability minus the negative probability. So that is ranged between 1 and -1. So here's the moment of the drift, and you observe that. So here's without drift. Sorry, you observe now that the sentiment gets quite stable as negative. And here, when you swap the sentiment, you see how the model learns to capture the new sentiment, which is positive, after some occurrences. So it gets unstable for a moment, but after some occurrences, gets stable again and learns the new sentiment of the word. That's what we did. Okay. So we're currently working on extending this work on trying to also implement a framework similar to WEFE, in which you have different methods for training incremental embeddings, and you can then track how the meaning changes over time. And we're extending the simulator to not only sentiment, but also other tasks that are usually used for evaluating embeddings, like analogies, semantic similarity, and so on. Okay. And that's the second part. And I will go to the final part of the talk. I will talk about polysemy, which is the third limitation of embeddings that I described at the beginning of my talk. So we create this model called PolyLM, a Polissimus language model. So what's the idea of PolyLM? It's a language model capable of automatically learning multiple meanings of a word. So as I said, words are polysemy. Many words are Polissimus. For example, you have the word apple for the fruit, apple, or you have the word apple for the company. So if you use things like word2vec, which is what we did here, you obtain static embeddings, and that means you conflate different meanings. Happens that is that you get unrelated words to be close together, left and wrong, for example, left and wrong. And the related words will be further apart, like east and right. But if you can get multiple representations for a word, you can expect, that's what we did, that each different representation will capture a different meaning. And that's what we did with PolyLM. And we can show here, for example, that you have left and right here, but here you have right with wrong, here you have left and leave, you have left and remaining, you have right, left, east, and west. So you obtain much nicer representation. So this can be done nowadays using things like contextualized embeddings like BERT, but they don't give you explicit representations. They give you contextualized representations. So for every sentence, you have different vectors. What we try with PolyLM is to obtain explicit representations. So to give the model the ability to actually have multiple word vectors for a word, and to force the learning system to allocate the different meanings into different vectors. So how we did this is basically PolyLM is an unsupervised language model, very similar to BERT. So BERT is a transformer encoder, which is a very popular machine learning architecture that is trained in a self-supervised scheme using a task called masked language modeling. What's the idea of masked language modeling? You have sentences, you remove some random sentences within some words within a sentence. That means masking, and you make the model to predict the masked words. And that's where the supervised signal comes. And this is done using a transformer encoder with multiple layers, and you expect that the self-attention forces the model to contextualize the words and obtain contextualized representation. So we took this architecture, but we make some modifications. With the first modification we made was that to make the assumption that the probability of a word occurring in a given context is equal to the sum of the probabilities of individual senses. So we say here that each word has a set called S sub W, which is the set of senses, and the probability of a word given a context is the sum of the probability of the senses if its sense given a context. That means that you don't have only an embedding matrix here, you have something like an embedding tensor. So you have multiple vectors for each particular word. So then we create a very sophisticated loss function to force to obtain the Polissimus representations in the different vectors of a word. So we combine standard language modeling loss, which is a cross-entropy loss of the mass words, with a distinctness loss that encourage one sense to have a high estimated probability of occurring and the rest to have a low probability. So this is an overview of the architecture. I won't go into the details here. The details are in the paper. We can discuss about them later. But we have basically a loss function that combines different components. And what these components try to do is to force the model to disambiguate the word by its senses, and to force to give always a very high probability to the most probable sense identified in a sentence. So this is done by exponentiating the log likelihood function. So we tried this model. We studied this problem in a task that was very handy for this problem, which is called word sense induction. Word sense induction is the unsupervised version of word sense disambiguation. So the idea here, you have sentences, you have words in these sentences, and you want to identify the sense of the word. But instead of doing a supervised fashion in which the senses are given, here you try to do it in an unsupervised fashion. So here you're allowed to determine by yourself how many senses you want to assign for each word, and all the evaluation is done by comparing like fuzzy sets. Anyway, we tried our model here. We developed two versions of it, a base and a small. A base is more comparable with the size of bird. It's even small, but still smaller in terms of number of parameters. And we obtained competitive results in SemEval 2010, and on SemEval 2013, we obtained state of the art. We were able to beat the state of the art. So that was quite nice to show that this architecture that produces explicit representations for senses was particularly useful for this task. Okay, and this was the work we did on Polysemy. So just to give some closing here. So we have presented 3 research projects, each addressing a different limitation of word embeddings. One about fairness, which was the Sweffer project. Another about how to make them dynamic using incremental representations, which was applied to the domain of sentiment analysis. And the third approach was this idea of having a language model able to capture the polysemy of words. So all this work was conducted with my amazing co-authors. I have Alan, Arun, Jorge, Pablo, and Bernhard. So I really thank all of them a lot for this work. I couldn't have done this work by myself. So of course, there is plenty of room for further research in these 3 areas. So I hope I have at least motivated one of you to, I don't know, start working on this field. So that's it. I'm happy to receive questions, and thanks again for the chance for inviting me to give a talk here.
Thank you a lot, Philip, for the nice talk. I find it very interesting and very inspiring. Despite myself, I do not actually come from the NLP field. So for the audience, in case if you have any questions, you can either raise your hands or unmute yourself, or in case you don't want to show up in this video. So I remind that we are actually recording the video. So in that case, you can also type your questions in the chat and I can read it out for the speaker. So at the meantime, in fact, I have a couple of questions. So the first one is, I think, Philip, at the moment you introduced the sentiment analysis. So from what I understand is actually you try to make the classifications for like people's motion to like anger, positive, negative. So I was wondering if you have considered, so by a natural way, there might be some sort of correlations, for example, between anger and negative, for example, or fairness, something like that. So I was just wondering if this correlation has been taken into account in the model when you're performing the loss function or the analysis.
Yeah, good question. Not in this work. This work was very simple. The idea was just to predict a sentiment of words because our target was to model this more that streaming setting. But on other of my works, I've done more things with emotions and multi-label annotations and these things. I actually co-organized a shared task on SemEval, which is a very important event in NLP. And we organized a shared task on emotion analysis. And then we did like multi-label annotations. So here you have tweets. We annotate tweets by multiple emotions simultaneously, like anger, fear, sadness, joy. And yeah, you see that some models can that leverage the associations between multiple emotions, can leverage that in a positive way.
Okay, thank you, Philip. So as you mentioned Twitter, so I was thinking maybe these kind of like amazing tools that you have developed maybe can use for real-time analysis for, so I'm not actually quite sure, but maybe that can be used to predict or to like nowcasting some kind of social events, like since you have a way to inspect people's motions on Twitter, you know that they're angry or they're like positive or negative. So is that possible, like to use this kind of methodology to predict some kind of social or natural events? So this is more like a question by Chris. Sorry.
People do it a lot. Yeah, a lot. You do lots, huge body of work on, like, there's even conferences on this, like weblogs on social media that works at computational social science, in which you see people applying ML models to social problems, and yeah, lots of things. And social unrest. We did something now. We published it in social web and social media in this social unrest that we have here in Chile, 2019. We got tweets from the network. We tried to study polarization, and we use these embeddings, for example, to study framing. So how different communities observe the same concept. You know, you have social unrest, and where people were in favor of the police, another very against the police. So we managed, for example, to do that with embeddings. So we train embeddings and we disambiguate them for the different communities. And you were able to observe, for example, is this word more positive for community A? Is this word more positive for community B? And we were able to visualize all these things. Yeah. So that's lots of work on that. Lots of work on that.
Okay, thanks. Yeah. In fact, for us, like more coming from the physics side of like either machine learning or numerical methods, it's quite amazing for us to see that using these methods, actually we can more like predict the things on the social side as well. Yeah, thanks. So let's see from the audience if there is a question. So as I said, you can either unmute yourself or you can type your questions in the chat. So if not, actually, I have one last question from my list. So I was simply wondering, so you have introduced like these different aspects. It seems like you have like a good idea or like initial points for all these three different aspects. I'm thinking, is that possible to combine them together in one big model if it's not like the things we already start to do?
Wow, yeah, that's a big topic. Yeah, I really would like to use I have the feeling that the models that can be used for polysemy can be used for example, semantic change detection. I've worked a bit on semantic change detection. This is a streaming setting, but we organize a shared task now in which you actually study them in a more linguistic way. So you have old corpora, like words from sentence documents from 2 centuries ago and modern text. And then you want to establish automatically the words that have changed their meanings. So my feeling is that polysemy is very related to that. So you have a model like this that can detect senses. Probably you could just concatenate 2 corpora, old and modern, and observe senses that are discovered to be different in one corpus and another, and use that as a proxy for semantic change detection. So I feel that maybe that's a possible way to combine these methods, but I haven't done it. And the same for fairness. Probably you could, I don't know if that would happen, but probably you have a very stereotypical corpus or hate speech corpus or this kind of data, and you apply these models that can in an unsupervised fashion identify senses of a word. Maybe the senses could go beyond the more traditional linguistic definitions, and maybe they could capture this kind of frames, you know, that this word means this for this community, but this word means something different for this other thing. And it's not something you find in a dictionary, it's something that represents individual perceptions. I haven't done it, but I think these things are related. Yeah.
And as you suggested, maybe when you combine these different tasks, you can identify new tasks, things like there's subtasks once you combine these different like combinations, right?
Yeah, definitely.
That sounds very interesting.
Like a big topic, but yeah, I think could be done. Yeah.
Okay. Thank you, Philip. So let's see if there's no question. Actually, I don't know why, but usually people have more questions. I think today maybe they're more shy than normal. Okay, so as I said, like we will also put our videos on the website, and so in case that people have questions, you can contact Philip by email, for example.
Definitely. After the seminar. Right now. Yeah, okay. Definitely.
So I would like just to thank you again, Philip, for accepting our invitation and for giving this very nice talk. And thank you for the audience to join us. So I wish everyone a good evening for people in Europe, and for Philip, have a nice afternoon then.
Thank you very much.
Hope we can see you later, like in person after the pandemic.
Definitely looking forward to. Thank you very much. Have a good night.
Thank
Bye.
you, everyone. Thank you, Philippe.
Yeah.
Bye.
Bye. Bye.